Hello again. So back in 2017, David sent me this EEVBLOG 121GW meter. This is one of the first prototypes. Originally, when I received the meter, the firmware was old enough that it didn't identify, and the Bluetooth on this meter did not work. Somebody had provided me with the image for the BLE interface, and I got the adapter to reprogram it. This meter is now 100% fully functional. Of course, I had transient tested this meter and I damaged it, so I spent some time going through the design, figuring out what the weak points were, and I ended up changing the design of the meter just slightly, and I disclosed all that information to Dave. I figured he could pass that on to UEI if they wanted to. So I've been wanting to run a production meter since he's released it. So what I have here are two brand new meters. The package just arrived today. I thought what we could do is just go ahead and open them up and let's have a look, make sure that they weren't damaged in shipping. Doesn't look like the boxes are crushed. Looks fine. Have a look at box number 2. Looks good. Now there was supposed to be some fuses that came with these. I ordered a package of them. Cost like an additional $20-some, I think. I've used those fuses before. They held up fine, so I thought I should just get some additional ones. They are not in this box. Let's have a look at the meter. You can see they have their silica gel pack. Looks like it comes with batteries. So it comes with the same firmware that I had installed on my prototype meter. Let's have a look at the second one. And right here are the fuses. So we didn't forget them. Everything looks good. And we can go ahead and power this one up as well. Yep, 157 as well. So I expected the two serial numbers to be sequential, but the one on the right is 72 and the left one here is 83. So due to the potentially destructive tests that I performed, I purchased 2 of the 121GWs, so I plan on keeping one of these in pristine condition. Basically, the problem that I run into, not just with the 121GW, but all the meters that I look at, typically people will have follow-on questions, and when answering questions like that, I typically have to post some kind of disqualifier, basically saying that the meters have been exposed to various transients. Some of them may have been damaged and repaired, some of them have been modified, so I just try to make it very clear what the state of these meters are when I'm giving answers as far as how they perform after they've been exposed to these tests. So I thought in the case of the 121, if I just keep one of these basically as a virgin meter, the way it was supplied, that'll allow me to answer questions about the meter after I release these series of videos. And we'll just start out in the DC mode. This should be roughly 5 volts. Looks fairly close. Again, this box is using this Apex VRE 305 reference. Let's just try it with an AC waveform. Again, this is capacitively coupled. See, it reads roughly 0. That's correct. Let's switch it to AC mode, and this should read roughly 2.5. That is correct. This is going to be DC coupled, so again, this is switching between 0 and 5 volts. And it should read 2.5 volts as well. And you can see it's at 60 Hertz. That's correct. This should be at roughly 30 Hertz. That is correct. This should be 15 Hertz. That is correct. And this is 120 Hertz. And that is correct as well. This should be roughly 70 volts. That looks fine. And you can see it's 3.2 kilohertz. That is correct as well. Let's just change this to AC plus DC. This should be roughly 90 volts. That looks good. This should be roughly 20 millivolts. That seems fine. And this should be roughly 500 degrees Celsius. That looks fine. Let's just go ahead and adjust this down. This should read roughly room temp. Yep, 22 degrees. And this should read roughly 1040. That looks fine. Let's just try it in the frequency mode. Again, this should be 60 Hertz. That looks fine. And this is again DC coupled. That looks fine. A lot of the meters have trouble with this waveform. Again, because it's biased around 2.5 volts. Again, that's 30 Hertz, 15 Hertz, 120. It's interesting how fast this is compared to using the AC input mode. This is in period, so at 60 Hertz this will be roughly 16.6 milliseconds. Looks fine. Let's just try it in resistance mode. And this is with the leads open, and this is with them shorted. That looks fine. Let's try it with an open. The meter's quite slow. Again, there's a short. I remember that when I was testing the prototype. It definitely isn't very fast. And if you follow Dave's videos, he had made a review on a Keysight meter, and one of the things he talked about was how slow that meter was with auto ranging, and they blamed it on the chipset that they used. And if you look at the schematics for the 121GW, they ended up using the same chipset as the Keysight meter had used. That was one of the things I was actually surprised of when I looked at the schematics for the prototype. So let's just try this with a 1 ohm resistor. Looks fine. Again, this is a 1% part. This will be 50 ohms, and this is 0.1%. Looks good. This is a 100 ohm. Again, this is a 0.1%, and this is a 1K. Again, this is 0.1%. This is a 10K 1%. Looks fine. This is a 100K 0.1%. It's interesting, it had the right number and then it slowly drifted down. Let's try this as a 1 meg 1%. What's going on with that? Let's just open it up again and try it a second time. Wow. So again, 1 meg 1%. This is extremely slow to settle. It's odd, it's not very accurate. I'm not sure what's going on with that. Let me just bring out one of the Bryman BM869s. Again, we'll use the same leads. Again, this is our 1 mega ohm resistor. There you have it. So yeah, I'm not sure why this meter is so slow. Let's try it one more time here. Sure. What the heck? Is that the switch? Wow, I don't know what that was all about. Oh, it's quite a bit better now. I wonder if the switch is just a little intermittent with this meter. Sorry about that. Let me go ahead and pull these off of there. There you go. Alright, so again, this is the other brand new meter. And let's just try that with the same 1 mega ohm. Here you go. Again, very slow to settle. This one seems better than the other meter. I wonder if there's just some debris in here that's kind of working its way out, or maybe the contacts needed a little bit of cleaning. Alright, let's just try this with a 10 mega ohm resistor. Again, this is a 0.1% part. This will be diode check mode. Here's a single diode. Looks fine. Here's 2. And let's try it with 3. Let's try changing it to the 15 volt excitation. And there you go. You can see the LED lit up. And you can see it's dropping about roughly 4.15 volts. You should be able to verify that with the Bryman. Let's have a look. Well, it's off a little bit. Not too bad. This is a 150 picofarad capacitor. Really? You can't pick this up? Huh. That seems unusual. Let's try it with a 1 nanofarad part. It's off by quite a bit. Let's try it with a 0.1. It's fairly close. Huh. Let's try the other 121. Thought for sure these could read down that low. Let's just see again. So change our mode to capacitance, and again this will be 150 picofarads. Huh. Let's just try it with the relative mode. Yeah, 51 picofarads. You know, just for a reference, again, this is the prototype 121. Let's have a look with it. Again, same version of firmware. And there you have it. 142 picofarads. And again, this would be 1 nanofarad. Fairly close. And 0.1 microfarads. Looks really good. Let's go back to the production meter. Fairly close. Here's our 1 nanofarad. It's definitely low. And our 150 picofarads, and again reading 0. Now again, what ended up happening with this meter is I wanted to upgrade the firmware on it at some point, and that basically forced me to realign the meter. So it looks like this meter is now a little bit more accurate than the ones that we purchased. Let's just try some of the other values. Again, this will be a 1 microfarad capacitor. Looks dead on, actually. Let's try it with a 10 microfarad. Looks really good. And this is a 100 microfarad. Looks good. Let's go back to the resistance mode real quick. Again, this is going to be a 40 mega ohm resistor. Looks really good. Let's try it with 100 meg. You cannot read that. For me personally, I do use higher value resistors, and I do like having that conductance mode, and I would have liked to have seen that feature on this meter. Let's go back to the 1 mega ohm resistor now that we've cycled the switch a few times. Let's just see what we get. Well, look at that. That's pretty decent. Now, again, I think that there's probably just some debris or something inside of this switch that's causing this particular 121 to have some issues, but that looks really good now. Again, let's try the 10 mega ohm. And again, this is a 0.1% part. Looks pretty good. Again, it's just taking a long time to settle. Let's go to current, and this should be 100 microamps. Boy, dead on. You can't ask for anything better than that. This will be 10 microamps. It's off a little bit, not too bad, and 1 microamp. And just for fun, let's have a look with the Bryman BM869. Again, this should be 1 microamp. See, our Bryman's dead on. Yeah, our 121's definitely a little low. Let's just try that with our second 121. Again, this is the current production one. Huh. It's pretty strange. Again, I would have thought that that would have been a lot closer. Again, just for a comparison, this would be one of our Fluke 189s. You can see roughly 1.1 microamps. Again, this is with 10 microamps. And here's 100 microamps. So it looks like the 121s are off a little bit in the current. Not too bad. It's one of the things I've been very curious about, is how this new meter is constructed compared to the original one. So again, this meter is one of the ones we just purchased. You can see it comes with Duracell batteries. This is obviously our prototype. You can see this is one of the ICs that I've saved that I damaged. This was the original part that was included with the meter. Again, this was a note from Dave about the Bluetooth not working. Of course, I've gone ahead again and reflashed that part, so this meter does have Bluetooth now. Before I got the Bluetooth working, I data logged strictly to this flash card, and I was pulling this card in and out. So of course, you can see it's very difficult for me to reach in here and grab this thing. And what ended up happening is I cracked this card holder. I'm actually surprised I never broke this thing all the way off, because you can see it's just kind of cantilevered out here in space. There's no support. And the new meter is essentially the same. You can see it just hangs out here in free space. I don't know if they've had any trouble with it. Again, once I got the meter working with the Bluetooth, I stopped using that card. I'd much rather log using Bluetooth anyway. You can see the shielding is basically the same between the two meters. It looks like the springs sit up a little higher on the production meter than the original prototype. Maybe the mold here has changed just a little bit. You can see where this one's smooth, and on this one we have this crosshatch. Other than that, I don't really see a big difference. The spring contacts look about the same between the two. That is definitely one of the problems with this meter, is you'll end up with the springs off to the side. I've seen other people post pictures of that. I've certainly done that as well. Put the batteries in and have the spring pop out. This one here, you can almost see how it's bulging out of the side. Same thing with the one in the back. Looks like they're using the same fuses as what the prototype had used. Notice the R network here. On the prototype, you can see I put a little bit of glue on there to try to help support that. Again, I was just a little concerned that I may shear that thing off. So one of the things David mentioned was, you know, of course they had to add this shim. And here you go. There's our shim. And you'll notice that the original prototype does not have that shim. You also notice that the molding here is slightly different between the prototype. Of course, the lettering between the two looks the same. It could just be some kind of a quality when they set up the mold, but I don't see any other differences in the case or the switch assembly. Of course, the circuit board is the big one, so the claim is they had to put the shim in because of the thickness of the circuit board. Here's another big difference is, notice the shield. Of course, the prototype does not have that. So the claim was that they had added this shim to make up a difference for the thickness of the circuit board. So I'm guessing this circuit board is quite a bit thinner than the prototype. Let's just have a look. So 53.5, and let's see what we are over here. 52.5, 53. We'll check it in one other spot, maybe up here. Looks like about 55.5. So what is our prototype? Boy, not much. 57, and it looks like 55.5. It looks like about 58. Let's recheck that with this guy. Yeah, so 55, so maybe 0.003 or so different between the two. Not enough that I would think that that'd make a difference to add this shim. Again, the shim's thickness, well, yeah, that's about 35 thousandths, and there's definitely not a difference of 35 thousandths between these two circuit boards. Let's just see if there's a difference in the height as far as where they're preloading this with that spring contact. Again, what I want to do is just get this where it's resting against the switch. Maybe 175 or so. Let's have a look at this one. We'll check in the same location. Boy, yeah, I'm gonna say once these switches have been installed into the 2 meters, that spring preload looks identical between the two of them. I would have thought essentially that face here floats off of this face here. So I'm guessing what's happened is that they wanted to actually push on this thing a little bit to add even more tension. I'll tell you, the thing I don't like about that is again, with the amount of debris that I saw with the original prototype after, really not cycling at all, is what would happen if I cycled the switch on this particular meter. So what we're going to do when I eventually do cycle that switch is I'm not going to be using this particular meter because I've had it apart. What I plan to do is actually cycle the other production meter, and I'm planning on leaving this switch assembly together. So what I don't want to have happen is to have people be concerned that I've taken this switch apart and then I went ahead and cycled it. So we'll do it on the virgin meter. So let's have a look at the switch contacts again. This is our prototype. And you can see the contacts basically look like beryllium copper. I was pretty concerned about this switch. I had sent Dave over pictures of the prototype because I didn't put a whole lot of cycles on this meter, and when I took it apart after I damaged it, I noticed a lot of debris where the contacts were grinding. So I know they tried to address that with this production meter. Essentially the loading on the spring here that holds that through the circuit board. This is a lot tighter on the new meter. You can see the difference in the contacts though. The one being plated, the other one not. You can also see the contacts on the original prototype use 2 dimples. So you can see there's one here and one here. Notice on the production one it's a single dimple. So they have changed that contact design. That does not surprise me. If we just look at the resting height of the dimple, looks like about 0.203 inches. So we'll look at the prototype. Looks like about right here, 202. And let's check the other side. Right about there, maybe 205. And again, this is our prototype meter. Again, I'm not trying to compress the spring. I just want to bring it down right where it rests on the contact. And about 208. So I'm not sure, to be honest, what the point of the shim here is, because I would have thought that the resting height or the preloading of the springs was set by this ridge here where this locks into the circuit board. The board itself looks good. I don't see what was causing this thing to go intermittent. It doesn't look like there's any debris or anything on the contacts. You can compare that with our original board. Looks roughly the same. One of the things that you'll notice on the 2 meters is that the vias are not located in the center of the pad. It could cause excessive wear. The other thing you'll notice is there are no traces that run between the pad. So for example, in some of the meters you may see a trace routing between one of the inner pads to the outer, and what can happen is over time you wear away that solder mask and you'll actually short the switch out, or even worse, maybe cut a trace. So you don't see that with the 121. Well, I think that's going to be it for part 1. My plan is to try to keep these videos a little shorter, maybe about a half an hour each. So in the next video, what I'm going to do is go over some of the circuit design changes between the 2 meters. Again, there's definitely been some updates to the hardware, and that's been another thing I've been quite interested in, because when I transient tested the original meter, it didn't perform very well against my tests, so I tried adding some additional circuitry to try to make the meter more robust. Also, I thought I'd comment, you know, this channel now has over 10,000 viewers. To me, that's just crazy. Again, I don't ask for people to subscribe. I don't run the ads or anything like that. There's a reason for that, and that's because I don't want to see a bunch of ads, and I'm sure you don't want to see them either. Again, this channel isn't here for any source of income. I just buy these meters out of pocket, so these meters were not donated by Dave like the original prototype. I paid for these out of pocket, and I've had people over the years that have asked about donating to the channel. You know, I appreciate that, and I'm glad that people enjoy the channel. Well, I think that's going to be it for part 1. Stay tuned for part 2, where we have a more in-depth look at the hardware differences between these 2 meters. Later.